Dave's Guide to Immersion in Virtual Worlds. So hopefully by now you've realised to a certain extent that visualisation in GIS is limited. I mean, it's got some really good stuff, especially for cartography, obviously, which is what it specialises in. But there are limitations in things like 3D modelling. For example, if you've got a point cloud of observations, a point cloud in 3 dimensions, there is no mesh function for doing a mesh in full 3 dimensions. There is no function for that. Animation, it's relatively easy to do straightforward animations, especially with a single data layer or multiple data layers. But as soon as you start changing colours, changing styles as the animation progresses, it becomes more and more difficult to do. It's true, I haven't really played around with those animation tools for the last couple of years, so I'm sure they're improving, but compared with animation software, it's relatively restricted in that respect. Interaction is very rich for a skilled user in something like ArcGIS, but for non-skilled users it can be a real problem, especially first years. If you remember back to your first year classes, what do you do? How do you interact with the data? Similarly, it can be usability. Usability can be difficult. Interaction is just one component of usability. And of course, we've got cost. Certainly, ArcGIS is quite expensive to maintain. So there's a whole number of reasons. Plus, it's a very large piece of software that's maybe not suitable for many environments where you want people to interact with your data, to visualize, see, and interact with your data. There's a lot of overkill there. So I'm going to talk about a few other solutions, some general solutions, or solutions for visualizing spatial data, and particularly give one example of 3D animation software being integrated within games console technologies. And then we're going to touch on or deal with augmented and virtual reality systems as well, which provide much richer visualization environments. So what are we talking about? Well, what do I mean by a virtual world? Here's just a few examples that I thought I'd stick up. Second Life, I've never actually been in Second Life. Got too much of a first life to think about a Second Life. Second Life is a virtual world where people create their own avatars, personas, and get up into all sorts of stuff. Be warned, if you type Second Life into Google, the images that you get back are not generally of this variety. It seems to be, a lot of people seem to do, I don't know, you get lots of pictures of naked avatars and things like this. This seems to be one of its prime activities as far as I can tell. Anyway, so Second Life, a virtual world where people interact with each other and do whatever else they do. But there's lots of other virtual worlds. My son got Minecraft for Christmas, so I'm just beginning to learn how to do Minecraft. This is the Ordnance Survey. The Ordnance Survey have copied their entire UK maps onto Minecraft, and you can download them into. What's Minecraft? Oh, sorry for the ignorant people. For people who are, I was ignorant until a few weeks ago. Minecraft is sort of Lego in the computer. You have these blocks of different types, and you build a whole world so people interactively build whole worlds out of these blocks. I've only just learned how to survive a night and not get eaten by zombies and spiders and things like that. So it's like you can see it a very blocked world here. There's a video, if you go and watch it on YouTube, there's a video there. This is Snowdonia in Minecraft. They've taken the digital terrain models and I think the Meridian data, exported it or converted into a Minecraft model, all these little blocks. And then you can go and wander around in Minecraft and go and destroy these, dig holes in the rocks, dig holes in the rocks. I think the Danish, I read the Danish did a version of Denmark and put it online, and then people just went round and trashed it within a few days or something like that. There was a mass sort of trashing of this Minecraft world that the Danish government had paid for. So this is, I wondered, I was trying to work out why they'd done this. I mean, and I presumed it's a combination of just entertainment and education, but somebody with a bit too much time, or outreach, it's outreach, it's whatever, anyway. So there's another kind of virtual world. Here's another example of this sort of visualization technologies being used. In this case, this is sort of in the real world. I think this is, if I remember correctly, I think this is the temple at Marathon, where the original Olympic Games occurred. So, which I've actually been to a long time ago. So here's one of the temple complexes, and they have been developing technologies or visualizations that recreate the original technologies, or the original buildings as they were when they were complete upon the site. So sort of visitor experience uses. This is a art installation called Border Memorial, and it uses, well, this is an example of augmented reality. So you've got your smartphone, here we are, this is the fence between Mexico and the US, and at various points along the fence and elsewhere in the landscape, they put those, I don't know what they call those square things that you scan, I can never remember what they're called, the Q codes, yeah. And you scan those at these locations, and you get on your phone, you get this sort of virtual reality skeleton. These are locations where bodies have been found of people trying to migrate into the US, and there's hundreds and hundreds of these places out on the landscape now where you can scan in and you get these skeletons. It's a memorial, it's an artwork. The British Geological Survey uses virtual reality technologies. If you go to the BGS, the British Geological, they have an open, they have a visitor centre where you can come in and they do a demonstration of using the VR technologies. You get your headset on, they show you the geological maps of the UK in 3D, 2D. So this is both for as a user, as a sort of educational thing for visitors coming to the Geological Society, but they use exactly the same equipment to do their own scientific investigations as well. Here they are looking at high-scale terrain models in 3D. This is another example using decision-making. This is a company called McCamley, who did a study with the University of Warwick. This company makes these innovative wind turbine technologies, and as you probably realise, there's a lot of reactions against wind turbines around the world, probably more in the UK than anywhere else, not in my backyard. So what they did was they set up a system VR system, which allowed people to see these things in various positions, see them operating in virtual reality, and to see whether they could improve the public's perception of turbine technologies once they'd experienced them directly in the real world. If your next door neighbour wants to put one of these turbines up and you're very against it, if you can see it in a virtual reality environment, maybe you get a better appreciation for what your neighbour's trying to do, which might improve your view of the technology. So, for example, they did a study here, participants' perceptions of wind technology before and after they'd seen the technology, seen the virtual reality reconstructions, and basically they got much better, they got significantly different performance once people had seen the technologies in action, and they hadn't. Indeed, when I went to the University of East Anglia many years ago, I saw wind turbine simulations being run there, And apparently I seem to remember them saying that people's responses to wind turbines were up to, or when they took various groups of people into the VR lab and they showed them the wind turbine technology, and they showed them both with the turbine still and those with moving. And apparently they got about a sort of, a twice as much positive response when the turbines turned when they didn't turn, just in the VR environment. So how people experience these things makes a difference to their the outcome of looking at this stuff. So these are just a few different examples of the kinds of technologies that I'm talking about, and they all use different technologies. So these various technologies, they address various of the problems that I mentioned initially with sort of GIS. The quality of the animation, the availability of data models and stuff like that. So and also things like widescreen view. So, you're working on a computer, you've got a screen that's that size, whereas if you're in one of these VR suites, you're talking about a whole room where you've got stuff projected on the walls and everything. And what this kind of technologies allow, this sort of VR caves, and I'll explain a bit more about what they are in a bit, and sort of headsets with 3D glasses on things, is that they stimulate the feeling of immersion. I think this is one of their most important factors or benefits, is that your perception, immersion is the perception of being present in a non-physical world. So it puts you you're not looking at something on the screen that's exterior to you. You actually become embedded in the virtual world yourself. You are sitting within this virtual space, or rather than being in the real world looking at something in the computer. So you actually go into these virtual worlds, and of course that's the Matrix film, isn't it? So this sort of stuff requires a lot of enabling technologies. And the different methods, the different approaches for doing it use different types of these technologies, but they all share the same sorts of things. You need some kind of visual display. And this could be as simple as a screen, but also headsets, handsets, or projective technologies. So a way of seeing the information, and we'll see how screens can be used in this context in a minute. You need you often have an aural or sound display as well. So it's not just vision, it's sound as well. Usually stereo sound, but in these special cave environments, virtual reality rooms, you can get full 3D sound as well. And one component of sound that maybe is not too familiar is the idea of haptic sound. So that's the sound you feel. So when you're in your dub reggae club and you're feeling the bass go through your body, that's a sort of haptic sound. And a lot of systems, they're starting to introduce this haptic sound as well into systems. Then there's haptic touch displays. So these are the main two. Most systems use both aural and visual. Haptic touch displays vary in sophistication from simple games controllers that, for example, the Xbox controller I have at home, somebody hits me with a hammer on some game and the thing vibrates in my hand as a response. But also things like gloves, the 3D gloves that people use you put a glove on, and then you can have sort of pressure sensors that pressurize your hand and things like this on this. Just at the very beginning is things like olfactory and gustatory stimuli as well. Really difficult to implement. How do you get smells? How do you release smells into these environments and taste into these environments? Scratch and sniff cards, maybe. So these are the sorts of technologies, and basically most systems obviously have visual display. A lot of them have aural display. Some have haptic touch display. Very, very few have the last ones. So what is immersion? Okay, so immersion is, so I've said it's that feeling of being inside the machine, so to speak. And games designer Ernst Adams identified 4 different types of immersion, obviously in relation to sort of gaming technologies. So he identified tactile immersion, which is to do with feelings and things like that, when you're controlling your game's controller and you feel, as they say, in the zone. So you're not really thinking perhaps about the actual actions that you're doing with the controller, you're automatically doing those. He also identified strategic immersion, which is where you're strategically thinking within the VR space, the virtual reality space. For example, chess players experience strategic immersion when choosing the correct solution among an array of possibilities. Narrative immersion we're all familiar with from watching films and reading books. In a sense, you cut out everything else, or you listen to the story or whatever. And obviously for us, we're interested in the concepts of spatial immersion, which wasn't actually listed by Ernst Adams, but it was identified by these Bjork and Holopainen, I would hate to pronounce that name, occurs when the player feels the stimulated world is perceptually convincing. The player feels that he's really there and that the simulated world that looks and feels real. So we're primarily, I think, interested in the last form of immersion, spatial immersion. I would question really whether for immersion whether the world needs to feel real or not, or just that you need to feel like you're inside this thing. It may be a world of data rather than, it always is a world of data, obviously, but it may be a world of graphs and symbols rather than a world that sort of tries to accurately recreate the real world outside. So this is an attempt. This graph is attempts to show the various types of technologies, or more right, not technologies. This is to do with a class. This is a classification of the different ways that you experience, or you can experience, reality and computer environments. I think that's maybe the best way of saying it. So on the horizontal axis, or let's start, no, so the vertical axis has 2 components. And this is called the dimension of artificiality. So basically we have the real world, the physical world, generated from the real world, or which is the real world. And then we have the synthetic or computer environment. So we've got 2 of those. And we are, in this virtual reality kind of situation, we are trying to connect or model the physical world in the computer environment and connect them together. And then the other dimension we've got here is what they call the dimension of transportation, which is where you are, so to speak, in your mind, I think, how to say it. So, for example, you could be local, in which case you remain in the physical world where you are physically, or remote, you can leave your body behind and go elsewhere, somewhere else. And there are 2 places where you can go. You can either go somewhere else in the physical world, in which case it's called telepresence, or you can go into a virtual world, which is probably more familiar. The other thing we can do is you might remain in one place in the world, but you might bring in information to your experience of the world where you are, in which case that's called augmented reality. So there and we'll see real examples of these in a minute. And this curve through here is often called the reality virtual continuum. If you're here, you're in the physical real world. You're in the real world. Here, you're totally in a virtual world. Your presence is in the virtual world. Your body or your mind is in the virtual world. It's totally in the virtual world. Augmented reality mixes the real world and the virtual world. So they're mixing them together. So let's just run through a few examples of these. Okay, so we're going to start off with game technologies. Game technologies, I don't think quite fit into this model particularly well, although they're sort of the simplest kind of technologies that fit on this sort of model. So in a game environment, you remain in the physical world. You're sitting there in front of the computer, and the virtual world is in the computer. So there's a kind of tie between you and the virtual world. You don't feel completely embedded remotely within the virtual world. You're sort of standing outside of it, but you're looking in on the virtual world in a games technology. Whereas in a cave technologies, because of the headsets and things like that, and we'll see those in a bit, you're actually physically, your brain is physically, and indeed your physical body in the case of a cave, is embedded within the virtual reality world. So, here's an example of a game technology being used for, in this case, a visitor experience model. So this is Fishguard. This is Fishguard Palace, which is a Roman palace down near, just outside Portsmouth, like between Portsmouth and Chichester, down on the south coast. Okay, and a student, Matt Smith, here at Kingston, and Nigel Walford, has built a 3D virtual model of Fishguard Palace as it was during the height of the Roman period. And the idea is this model is going to be displayed within the museum using within a game engine technology. So they're going to use a game engine, have a screen, and just have a little thing that allows people to navigate through this model. So game engines, what are they? They are software frameworks for constructing games. What a surprise. They have 2 or 3D graphics engines, depending on which software it is. Importantly, they have a physics engine or at least minimally some kind of collision management system. So it actually allows you to model physics in the system. So if you get a ball and you kick the ball or apply a force to the ball, it will move according to the physics that are programmed in, presumably Newtonian physics. It also has strong capabilities for sound and for animation technologies. And depending on the game engines, they might support artificial intelligence, network streaming, memory management, threading, all these things, or other things as well, which half of them I don't really know what they are. So game engines, things that you run games on, highly interactive. And of course you run the games, you write the game in the game engine, then you port it to a particular game's console, this being an Xbox. This is why, obviously, these are widely developed technologies, familiar, cheap, and support a high degree of interaction through the various games controllers. What's this? I have no idea. I'm on one of these. I don't know what the difference between that's Microsoft. PlayStation is somebody else. Sony. So yeah, I'm just learning the basics. It's all Xbox because I ended up buying an Xbox at Christmas. I am so, last time I played video games, it was virtually Pong years. It's a bit later than that. But it's a new thing to me. Okay, Fishbourne Palace, as I say, is down here. This is Fishbourne, so Portsmouth, a few miles down here. Chichester's up here, and some Roman tiles, as you can see recorded on this probably county series map, were located were found here, I think, in about the 1930s. And it is probably one of the largest Roman buildings in the UK. It's got some of our best, if not the best, preserved mosaics in the UK. This is the present museum situation. This is inside the museum here of the mosaics. So to reconstruct this model, Matt had to collate all the information, or a large amount of the information that was available on the palace, and particularly, obviously, the reconstructions of the palace. So he had base floor plans, and you can see the dark colouring is indicating the things that have actually been observed. The lighter colouring here is kind of guesswork. So there's a lot of missing information. There's solid information on walls, but there's also a lot of guesswork going on by the archaeologists as to what the true nature of the palace was, because it's either been destroyed or it's not been properly excavated yet. He had ground plans, and he also had front vertical profiles as well, again prepared by the archaeologists. Probably a lot of this, it's reconstructed on the basis of the materials found at the site, but also comparable buildings elsewhere in Europe. So it's some guesswork. Here's an example. This is showing the fragmentary knowledge, or the fragmentary nature of the evidence. This is a wall. This is a plastered wall, and you can see these are the actual fragments that have been found, and this is the attempt to reconstruct what the painting on the wall would actually have been like. So there's a lot of missing information. Similarly, here's a mosaic, one of the mosaics, and you can see the dark bit is the known, the observed, and this is the guessed mosaic. So he's constructed this model. You're constructing, some of you are constructing models in SketchUp. Matt used Autodesk Maya, which is a much more powerful version of kind of SketchUp, basically. And it's an example of 3D animation software. So it's got very strong support for 3D object modeling. Animation of those models. Also supports some simulation if you've got moving objects, rendering to video. But important for the application, which is a sort of museum-based application, it doesn't support walkthroughs through using a controller or something like that. So you can make the models, it supports the making of the models, their animation, their rendering to video, but not the sort of things that the game engine allows you to do, is to walk actually through the model using simple controls. So we built the model in Maya, very similarly to how you're building models in SketchUp. Initially putting the main structures, building the main structures, and then Maya supports a very rich set of tools for designing textures and things like that. So here's this is like the workflow used to create the mosaic itself. So it involves both identifying defining the grout that goes between the tiles of the mosaic, defining the mosaic tiles themselves, and tiling those tiles into the shape. So quite complicated texturing workflows to create various textures and things like that. To create this is the 3D, the VR model that he created. And then once you built the textures, you have to get them laid over the buildings correctly. So for example, here's the tiling on the roof. So initially, when you just slap the tiling over the roof, you got these artifacts. So these then had to be corrected to make the tiling. So I'm just saying it's a really fiddly business to create these models, involving a lot of peps. Once the model's built in Maya, it's exported, in this case, into the Unity Games Engine machine, which allows And then once the model's in there, then it can be rendered to the various game consoles. Okay. So let's page down. Okay, so that's my example of sort of gaming technologies, and you can see, unfortunately, he hasn't actually managed to get it fully working in a games console, so we can actually say. Okay, cave virtual environments. So, excuse the rather long amount of text on these things. So what is a cave virtual environment? These are defined as sort of wide field, as you can see a large area of computer-generated multi-sensory information. So they're multi-person, room-sized, high-resolution, or rooms with high-resolution projectors, 3D videos, and audio environments. They track the users in real time, so when you're wandering around in the cave. Has any of you been in these places? A cave, have you, not as in a cave underground, as in a cave technology. Go and see, try and find one and go and see one, if there's an open one in London. I mean, if you've been to sort of, possibly, I've never been to the one in London Eye. Yeah, it's kind of, but did you get, yeah. I mean, I think this sort of stuff in modern cinema technology, it's kind of in there now. It's, that sort of stuff is available, but it's well worth going to see one of these if you can. Certainly some of them a lot of them have open days and things like that. So it tracks the users in real time, so you get a little thing and it tracks how you move through the room. The graphics are projected onto the walls, floor, and ceiling of the building. So the ones I've been into, or one of the ones I've been into in Duke University, had all four walls and the ceiling and the floor were projected on. And you view those, and you wear stereo glasses while you're in there. So what happens is the software and the system, it detects where each of the people are in the room, and then it adjusts what's projected onto your viewing glasses and the walls and floor, the walls of the cave, on the basis of the position of various people. And these images are quite weird because they extend beyond, both within and beyond the walls. So you're standing there in this room and you're looking off into the infinite distance. There's no sense, you lose track of where the walls are. You can't see the walls anymore. It's like you're in an open space, unless of course it's being projected as a not all in space. So you can have a tile pattern going off into the infinite distance, tables and chairs going off into the infinite distance. And these things appear real physical objects until you try and actually pick them up and move them, and then your hand just goes straight through them. It's kind of weird, but they're kind of interesting. But if you've got wearing one of the 3D data gloves and it's suitably set up, and you can actually pick up the virtual chair and move it around. And if you've got a tactile glove, you can feel that in your hand. I mean, most weird. And one of the dangers, though, is that because you don't know where the walls of this place are, you can just walk into the walls of these things. So they're covered in rips and bangs and scrapes where everybody's crashed into everything, fallen over the table and what have you. Interesting places. Now I'm going to try and, oh God, it's going to die. It's going to go and die on me. Okay, I mean, I'm just going to say, look at this video. This video, I won't play it, but you look at it in your own time. It's really good example of using VR, one of these cave environments, in this case to do with forest fires. So people can see, they can fly over a fire. The firemen who are involved in this, they can fly over the fire. They can look down on it. They can look at it at different angles. They can wind the fire backwards. And they also use it for public information. So, for example, people get invited into the VR environment, and what they do is they generate a 3D model of that person's house and surrounds from satellite image data, a rough model of their house. Then this person sort of plays a game where they set fire to various set fires and things like that, and they see whether their house burns down or not. And apparently it has a huge effect on people's behaviour afterwards regarding in getting suitable fire insurance, also keeping down, restricting the amount of dead wood and stuff like that, fuel that's around the house, cutting fire breaks, all this kind of stuff. So they find it extremely useful, not only for training firefighters, understanding how fires move across the landscape and behave on the landscape, but also for influencing people's behaviour when it comes to fire. You hear about these tragic stories of people who stay in their houses, trying to protect their houses while the forest fires are coming towards them, and they end up dying. Well, if you've got an experience of a forest fire in a simulation environment, perhaps you'll run a bit quicker. Okay, so that's a sort of VR in its totality. You're in this cave, you're embedded within this 3D world. I'm just going to mention telepresence really quickly because telepresence is the concept of being somewhere else in the real world while you are somewhere else in the real world. So my examples of these things, like this is one of these robots they use for bomb disposal. So in this case, the robot goes off into the building or whatever, or a collapsed building where you've got rescue operations going, you've got cameras, gripper cameras, zoom cameras, all microphones. This is basically your remote body. And in this case, the operator experiences just through a screen environment. But you could see, you could put a headset on that, and you could wear have Google goggles or something like that as an alternative. But what it does is allows the person to be effectively somewhere else that they aren't. So that's one example of telepresence. Another example of telepresence is this idea of remote presence robots. Particularly, this seems to be taken up particularly in the medical area at the moment. So our doctors are obviously in great demand, and particularly in rural areas, you may not have quick access to various specialists and things like that. But if you have a presence robot, then the doctor can see the patient effectively and interact with colleagues from some other building, some other hospital, maybe hundreds of miles away, maybe in another continent. And indeed, with a robot like this, as opposed to just a screen, that person can actually control that and go and visit people in their rooms rather than just, be sort of communicating through a computer terminal. So there's more flexibility there. This can wheel itself into the operating theatre, and they can actually undertake operations using these technologies nowadays. So that was augmented reality. Oh no, so that's all I'm saying on telepresence. So the last one is augmented reality. So this is mixing virtual worlds or virtual data with the real world. Adding images, sound, touch, smells and tastes to our experience of the real world. So here's a load of examples of mechanics seeing instructions what to do next when repairing an unknown piece of equipment. Surgeons see ultrasound scans of organs while performing surgery. Firefighters see building layouts to avoid otherwise indispensable hazards, etc., etc. Augmented reality in 2010, this was in 2010, they were saying it was moving from the labs into industry in the consumer market, and I think that's it's still the case today. And it's particularly a new exciting area with today's smartphone technologies. So you have to, obviously have virtual objects georeferenced in a virtual world, and then you need to register those virtual objects in the real world and display them over the real world. And to do that, you need a variety of technology, and there's a variety of technologies that allow you to do this. So this is a picture of the world's first head-mounted display called the Sword of Damocles, which was developed in the 1960s. So the initial technologies go back to the 1960s. So we've got a see-through screen onto which they projected 3D graphics. And the technology has basically increased from the 1970s through to the present day. I won't go through that list in any detail. So today, for example, we have, a few years ago, I suppose it's a couple of years ago now, we had Google Glasses were the latest thing. They've now been dropped, I believe, and are no longer, it's a dropped project. Mind you, I think it was last month, Microsoft announced its version called the HoloLens. So this technology is becoming available for purchase relatively cheaply. Well, you may well know more than I do, yeah. I mean, I don't know much about the Google Glasses story, but it was clearly, so you think they've dropped it and decided that people are more interested in smartphones than they are in eye technologies, yeah. Yeah. I mean, personally, I looked at I mean, I've never seen them through them, but I mean, the thought, I mean, wearing glasses myself, the thought of having something flashing on the inside of my eye is just horrendous. But then maybe that's just because I'm old now. Okay, so most important thing about this is how the visualization is delivered. And there are basically three ways that you can implement this augmented reality thing. So you can have video see-through, which is where you've got a video of reality. So you video reality, and then you overlay the digital information on top of that video. You can have a see-through optical device that you project the digital information onto. Or the third way is that you project the digital objects or digital information onto the real-world objects themselves. So there's three ways of doing that. I don't know why True 3D, that was meant to be about sound, so ignore that one on a bit. So video see-through is the cheapest and easiest to implement because you're videoing the real world, so it's all digital. It's all being done digitally. And because it's all digitally done, so you've got a digital real world and a digital virtual world, is that you can easily match the contrast and brightness between the real world and the digital world. You can delete objects from reality, which is a really good thing, because you've got a video of the real world. If you can identify, say, the cars or the people in the real world as objects on that video, then you can delete them, remove them from the video quite easily. Disadvantage, though, is because it's video technology, you've got limited resolution, because it requires and quite often a limited field of view. And it can lead to user disorientation and visual discomfort through eye strain, the video see-through methods. Optical see-through is where you've got you're looking through a visor or something like that, and then the information is projected onto that visor. So that's much better in respect of the real world resolution, because you're seeing the real world, you're not seeing a video of the real world. Importantly, for certain applications, it's safe on power failure. So if you had a headset on and you were having video of the real world projected, see if the power went down, you're just in blackness. So if you're flying a fighter aircraft or in some sort of emergency rescue situation, you don't want the world to go black if the power goes off. So the optical see-through is a much better solution. Because you're seeing the real world, it's difficult to obscure things in the real world. Unlike the video where you can cut them out, you can't really cut things out of the real world because they're just coming through this plastic screen. So there are real problems with that. And there are actual systems, optical see-through, some systems which actually use low power lasers to draw on your eyeball on the back of your retina. Sorry, not on your eye, the retina being the light sensitive surface at the back of your eye. So then rather than displaying the digital stuff on a screen, they actually project it onto your retina, at the back of your retina. Fine, the third delivery method is projective. This is kind of good because you don't need any special eyewear, or generally you don't. You can use multiple projectors, so you can cover very large surfaces, giving a wide field of view. But to interact with these things, you'd need other kinds of input devices. These displays, these different types of displays can be positioned in different places in relation to the person. So for example, we can have, as we can see here, you can shine the digital information onto the retina and have a retinal display. You can display the digital information on a head-mounted display. You could have a handheld display, or you could have some sort of display in the room, so to speak, that multiple people look through. Yeah, I suspect so. Yeah, sort of more sort of communal things. And the projectors as well. So this is the projectors. If you're using a projective system, you could have projectors that are mounted on your head, mounted on your hand, or mounted spatially within a room. So there's all sorts of alternative options for display positioning. Here's some more of these headsets. This guy looks like a model. This one just looks like Mike. Here's some examples of handheld ones. Obviously, you know, these, you know, even if now, this thing, virtually everybody's got these things in their pockets, and yet 5 years ago it was still sort of cutting-edge technologies. And here's an example of here's the overlay of the VR. So this is video. So in a case like a mobile phone, you're taking a video of the real world, and then you're overlaying the digital information over the video being taken by the digital imagery being taken by the phone. Here's some examples. This is some examples of some handheld systems with a see-through display here, and various projectors and stuff like that. They're very fuzzy photos. They're rotten photos. Okay, so I'm just going to give you a quick example, I think a really interesting one, of augmented reality. And this is a study, I can't remember where these guys are. They're in this, but they've been developing a mobile augmented reality system for environmental monitoring. And they're doing this because there's a physical disconnection between field experience and desk-based analysis. And, you should be familiar with this. You go out into the field, you capture data, you record all your figures, or you maybe use a data logger, you maybe write them in your notebook, you come back into the lab, you enter that data into the computer, you look at it and analyse it in the computer. So you're looking, when you're doing your analysis and using the data that you've collected, it tends to be on the desktop somewhere, and you're looking at digital models that are less spatially and temporally accurate than on-site observation. They're a model, they're a generalization of the real world, and they only include what you measured or the other data that you downloaded. So they're a very restricted view of reality. So the idea is that if you can bring the visualization process, the models, the data into the field, then you can overlay the model data over the reality to give us a much richer understanding of the processes operating in nature. And this augmented reality provides, and they're using, that's quoting what the paper says, a natural way to display data on top of field locations. So it's got quite heavy requirements, this. So you need, obviously, your data georeferenced. You need 3D models of the terrain. You need network access, preferably. It is possible to use pre-recorded data, but if you're wandering around in the field, the last thing you want is some massive disk drive or something attached to you if you can help it. So it's best to have network access. It also means if you've got network access, you've got the access to the power of potentially large cluster computers and things like that running simulation models that you just couldn't carry around with you. So having a network access sort of increases what you can do. It also allows updates and communication with other users. You need accurate tracking. You need to know where the user position is, but you also need to know the other stuff where other things are in the landscape. So, for example, this is particularly one of their applications or what they use it for is for having real-time sensors, so they've got real-time sensors across the environment collecting data. You are the scientist wandering across in your landscape, in your study area, so that you look up the mountain and you know there's a weather station up that mountain. You can actually see the live data from the weather station projected over the point where the weather station is in the landscape. So that can be really, really useful, especially when you're looking at things that happen in the landscape in short periods of time, things like flash floods and things like that. You're watching a flood grow, and you want to know where the rainfall has occurred, and you can see that. You can get this information relayed to you over this system. It should have a degree of interaction. It needs visualization. User interface should be clearly visible, preferably show undistorted colors, etc. And importantly, it's got to be a robust mobile system. It has to survive field work in rugged conditions, and it has to be ergonomic, so it mustn't be it's got to be easily movable about the landscape. And also you must be able to use it using gloves and stuff like that. So they implemented it, rather than using fancy stuff, they implemented simply on a Toughbook, Panasonic Toughbook system. It has limited processing power, screen size, network bandwidth, but it's got a good screen and it's rugged and ergonomic. So they decided to go with existing technologies and adapt it to use. This is an overview of the architecture of the system. And as you can see, it's quite a complicated system. So it integrates on-site and remote. So part of the system is on-site and part of the system is in the remote network to the remote system. So in the landscape, you've got various sensors. You've got air temperature, snow temperature, radiation, wind, soil moisture, various sensors in the landscape. Those communicate over wireless network with the the data acquisition and management system running on a server back at the laboratory or wherever the server's running. Don't worry about these GSN nodes. That's all to do with integrating these various sensors. So basically the data is being collected by the automatic sensors in the field, gets fed back into the server where you've got a data acquisition and management system. Out in the field, you have your people with their tablets. The tablets can record video. They've got GPS, know orientation, so you know which way the camera on the AR is viewing. So those viewers, you also have on site a local kind of server. A local PC is set up with a wireless network, which allows it to connect to the tablets, the rugged tablets. What this is doing, the primary function of this, is that it allows local communication between these Toughbooks, different people at different Toughbooks. So for example, I go upstream, we've got a flood, okay, in the river. I go upstream to have a look at the conditions at a confluence upstream. My colleague goes downstream and looks at the conditions down there. Through this system, both these tablets on site are linked through a common shared wireless service. And what it allows is for me upriver to switch who I am to the person downriver, so I can now see what the other person is seeing and all the information that they're looking at, and vice versa. So it provides a shared view service where anybody in this network can see what anybody else is doing in that network, and indeed can manipulate the data overlays over the real landscape viewed through the cameras of the Toughbooks. It also has a link. We've got legacy data here, so here's the legacy data from the census and other information. That can also be fed through in the field, so from the field we can tell this to run various simulation and analysis models running on clusters and things like that. So we can do a model of our flash flood while we're watching it, getting real data, obtaining real time data from the sensor network at the same time. Oh yeah, it's a really nifty system. And this is an example of what it looks like on the screen. This is a really simple view. Here's visualizing the sensors in the field. I'm sorry about the quality of these images, they're not great. So here's a simple labeled view. Each one of these labels relates to one of the sensors in the environment. Here's an example where they've actually got icons, using icons to locate the various sensors in the environment. And you can clearly see you could size these by the values coming through the sensors at a particular time. And here's an example, it's a garbage again. This is alternative. So this is where you're overlaying contours over, or isolines over, over the landscape. So here we've got the underlying video of the real world. On top of it, we've overlain contours that have been correctly georeferenced to that landscape as seen through the camera. I don't know what they're isolines of. But notice this is showing two alternative ways of visualizing this information. In the first one here, the real world is kind of faded back a bit, and so that you get emphasis on the contours, whereas you can flip it where you get a sharper picture of the real world, so the emphasis is now on the real world rather than the contours. So you get these subtle shifts. They programmed in these subtle shifts to allow you to emphasize either the contours or the landscape, because it's very difficult to show both at the same time in equal resolution. That's just the final one, little image. So here's an example of two locations that they're doing using this technology, which I think is really good. So this one is in the Alps, and this is near Helsinki, Finland. This is to do with snow packs and avalanche predictions. So here's the site. Here are the various sensors, weather stations, snow depth measurements. This is the equipment they're using, and these are the kinds of visualization that are being made by the scientists in this field study area here. Here's a hydrological example. So it's a generic system that can be used for lots of different types of environmental situations. So here's a hydrological modeling where the sensors are to do with river levels and river flow. And this is sort of the kind of visualization that we're seeing. I'm not quite sure what that was, soil moisture or something like that.